All right, we are going to start 5.3, part 3 off with an example. Let's say we were looking for the general solution to this differential equation. Now, this one's only order 2, and we've been working with higher order ones, but it'll work to keep things a little bit simpler for right now. So we would write that characteristic polynomial, r squared plus 2r plus 5 equals 0. This one doesn't factor, so we will go to the quadratic formula to figure this out. And then we start crunching this out. We start running into some issues because we end up with r equals -2 plus or minus -16 all over 2, which means we're dealing with some complex solutions. And we can simplify the root first, and then now let's simplify these fractions. And we end up with -1 plus or minus 2i, and we have not talked about how to handle that yet. So let's do that today. All right, so let's take a look at complex roots. In general, we know they come in pairs. So if you have an a plus bi as a complex root, a minus bi also has to be a complex root. So how does that fit in with our solutions? Well, if we had before c1e to the r1x and c2e to the r2x for two non-repeating roots, now if we're going to switch and make these complex, you'd end up with a plus bi and a minus bi as your coefficients. So then we kind of go, well, what should we do from here? Well, we could split it apart into the real and the imaginary parts. So we're basically just using exponent properties to pull these apart a little bit. But we kind of do, maybe we do that and we look at it and go like, well, does that help? And that's kind of the question. So to look closer at this, we get to take a stroll down memory lane and talk a little about Taylor's series. Huzzah! Now, before you get too nervous, concerned, or annoyed, we aren't going to actually need Taylor's series when we tackle these problems. But I do want to take a minute. That's why we're only doing the video today. You don't have any homework tonight that goes with this. I just want to show you where it comes from, because otherwise it does kind of seem like it's a little bit out of left field. Plus, I mentioned before, one of the things I like about these chapters we finished the year with is they really do pull together a lot of math from previously in your math life, and it is kind of cool in a math awesomeness way to see all of these math pieces coming together. So Mr. Peterson will be thrilled that we talked about Taylor's series, even in this situation, even though you're done with Calculus BC. So, as you'll recall from the other day when you and your friends were not exactly hanging out this year, I suppose, but video chatting about Taylor's series, the Taylor series expansion for e to the t looks like this. Now, in our particular case, we don't have e to the t, we have e to the it, which tweaks it a little bit. Because that I is in there, it ends up getting raised to the nth power. And since it gets raised to the nth power, we end up with an I, then an I squared, then an I to the third, and those powers of I keep increasing to match the expansion for t. Well, what ends up happening with that is everywhere that we had an I squared, that becomes a -1. So that's why this is -t squared. All of the odd powers of I are going to, of course, end up with an I left behind. And then with the even powers, there's a little bit of an alternating that happens. I squared would give you a -1, but I to the fourth gives you a -1 and another -1 because you have I squared times I squared. So that ends up just being a positive term. But then we get to I to the sixth, and I squared times I squared times I squared gives you 3 -1s multiplied together, which puts you back negative. And it just kind of keeps, wrong one, which makes it negative again, and that just keeps flip-flopping. Okay, so now let's break this apart a little bit. If we look at the real terms, or the real parts, which is all the yellow stuff, and if we separate that from all of the green stuff, we end up with this. These terms gathered together plus I times these terms gathered together. Well, this is a big deal because this piece from here is the expansion for cosine t. And this piece is equal to sine t. And I know what you're saying. Sepala, just last week I was Insta-snap tweet texting that exact thing to my friends, and that is Euler's formula. And you were correct. If we have e to the I theta, or what we've been working with, e to the I times x from that second piece of the complex root, we can actually substitute, instead of e to the I theta, cosine theta plus I sine theta. Okay, so let's take a look where we're at now. We started with these two complex coefficients in our exponent. We talked about, well, we could split those apart into the real and the complex. And now what that means, because of Euler's formula, is I really have e to the ax times cosine bx plus I sine bx. And then when you have a negative in front, you end up with e to the ax times cosine bx minus I sine bx. But wait, there's more. So we come back to this original problem we talked about, like, well, here's what your roots would look like. So what happens from here? Well, we can make those substitutions. We still have c1 e to the a times x that gets pulled out in front. But then we're going to substitute this piece we pulled apart for e to the bix and slip in and substitute in the Euler's formula piece. And then we do the same thing with the second term. C2e to the ax. So the real part of our solution still shows up as an exponential. But then the imaginary part, we're going to substitute with Euler's formula. Okay, and then if I distribute that c1 e to the ax and c2 e to the ax, I end up with separate terms, no more parentheses. And then I am going to gather together the cosine pieces, which don't have any I involved, and the sine pieces, which do have an I involved. And remember, if we were actually working this out and there were values in here, we haven't done anything with initial conditions yet. So these constants are just constants. And we could just substitute in a value, but we're actually going to go a little bit further. If C1 and C2 end up being both 1/2, then you would just end up with 1 times e to the x cosine bx. Even here with this I, it could be that your constants that you end up solving for are imaginary. Well, if you ended up with a negative 1/2 I and a positive 1/2 I and substituted them in here, you would end up with negative I squared, or excuse me, negative I times I. Well, negative I times I is negative I squared, which is really negative, or the opposite of -1, which is 1. And so depending on what those constants end up being, we can actually get a little bit simpler version. So our theorem that I'm going to show you is all based on this and what might happen. The theorem says, if the equation that we get from our constant coefficient differential equation has an unrepeated pair of complex conjugate roots, we'll talk repeated in a second, but this theorem is an unrepeated pair of complex conjugate roots, then the corresponding parts of a general solution of this differential equation, where this came from, for the complex part, it's just e to the ax, e to the real part, times x, and then in parentheses, c1 cosine bx plus c2 sine bx. And that is not a mistake. We do not need to put the I in here. Because as we just talked about, if there needed to be a I in this formula for some set of initial conditions, it'll get taken care of when we go substitute values in. So we don't need to bother with it right now. We can just tackle it with all real values in there. So let's try one. So we're actually going to wrap up our example from earlier. And in that problem, we had gotten that our roots were -1 plus or minus 2i. So if we're going to apply this to that, our general solution would be y equals e to the real part times x, or you could just do -x in this case. Then c1 cosine the imaginary part times x. We don't actually put the I in there, it's just the 2. Plus c2 sine of 2x. And again, if it bothers you, like, wait a minute, how come we didn't have to include an I anywhere? It's because if the constants end up needing an I somewhere, that will show up when we do our initial conditions. And that would be it. So we're going to bypass setting up the whole problem from scratch. Let's just say we have -3 plus or minus 2i as our roots, and they have multiplicity 2. So when we're going to write this general solution out, you would still have e to the -3x for your real part. Then it would be c1 cosine of 2x plus c2 sine of 2x plus. All right, and then the last thing related to these theorems is not really a formal theorem in our textbook, but it's kind of putting together the ideas, and I just wanted to make them explicit so we can see that they work together. So I call it my informal theorem because it's not numbered in the book. If the conjugate pair a plus or minus bi has a multiplicity k, So that last theorem talked about if there weren't repeats. This is talking about if there is. Then we just put together the ideas of theorem 2, which is what we did with repeating roots, and theorem 3, which is what we're talking about today, or what we did in that last slide. Our general solution, if you have a conjugate pair of multiplicity k, is the first time through, for the first occurrence of that root, you just do it the same. Just use theorem 2, e to the ax times c1 cosine bx plus d1 sine bx. Then when we go to the second occurrence for that multiplicity, you just multiply by an x, but leave everything else the same. Now these solutions, or these pieces of the solution, are independent because we have that extra x, and you would keep going. You would go from x to x squared to x to the third, all the way up until your last term would be x to the k minus 1 times the exponential piece and the trig piece. The reason it's k minus 1 is, let's pretend it was multiplicity 4. If it's multiplicity 4, the first time we write the occurrence of that, we don't need an x at all. This is our first time we ever saw this. Then this becomes an x. Then we'd have an x squared, and we only need 4 terms. This is multiplicity 4, so your fourth term would only be up to x to the third. So let's try one here. So we're going to bypass setting up the whole problem from scratch. Let's just say we have negative 3 plus or minus 2i as our roots, and they have multiplicity 2. So when we're going to write this general solution out, you would still have e to the negative 3x for your real part. Then it would be c1 cosine of 2x plus c2 sine of 2x plus, and now here's where we add that extra x on so we can make this next version of this linearly independent. And then we should keep increasing our subscript here. And you can leave it like this. If you wanted to distribute that out, you could leave it that way. You could write it out that way too. But unless we're going to go further, there's no need to go anymore with the general solution. So this last example we're going to do doesn't have anything to do with the complex homework you look at that goes with this video lesson that you're going to do tomorrow. This is actually tied to a problem you're going to see in the following assignment where we kind of mix all the problem kinds together. And it's not anything complex. It's really just a factoring trick, and I just didn't know if you'd seen it recently, so I figured we'd talk about it quick. If we were to expand this out into the characteristic polynomial, we would have this. And the problem we run into is we don't have a great trick for factoring here. There's no GCF to factor out of all this right now. So there's not a trick. There's a method, or there's something you can try when you have 4 terms like this, where you split this down the middle, and it becomes 2r to the third plus r squared. And then we're going to look for the GCF of that piece, and we're also going to look for the GCF of the second half of this. And only the GCF from those pieces separately. So the GCF from this would be an r squared. And if I factored out r squared from the first half of this problem, I would have 2r plus 1 left behind. And then I look for the GCF of this piece. Well, here the GCF would be a negative 9. And if I factored out a negative 9, you'd be left with 2r plus 1. And here's the moment of truth and the magic. If this is going to work, here is where we would know if these 2 terms match. So it's called factoring by grouping, and here it works because they match. Sometimes you might go through this process and you end up with 2 completely different terms here. That just means that factoring by grouping doesn't work, and either it doesn't factor at all or you're going to have to find some other way to make it happen. And the idea with factoring by grouping is we're actually going to factor out our GCF here is actually that set of parentheses. So 2r plus 1 is like it's getting factored out in front, and that leaves behind r squared plus negative 9, or r squared minus 9. And now that can be factored further. So our fully factored version of this one here, whoops, not equals, is 2r plus 1, r minus 3, r plus 3. And then we could write our solutions. So when we go to write the general solution, again, this one's totally distinct, where all the roots are different, and we just write our solution. So again, not anything to do with complex, but that factoring by grouping, I didn't know when the last time was you saw it, so I thought I'd make sure I ran it by you.